Good evening. Tonight we welcome our speaker, Adam McMaster, an astronomer and postdoctoral researcher at the University of Southampton and a recently completed PhD student at the Open University. His work specialises in the use of citizen science to find rare and interesting things in large astronomical surveys. Currently, he is searching for the gravitational micro-lensing signatures of black holes in data from the TESS satellite. Adam was with us last year, October time, talking about the star that changed colour. So tonight, let's show our appreciation for Adam McMaster.
Thank you. Just share my screen. Hi, I'm getting a slight echo. If you wouldn't mind muting at your end. Thank you. Right, let's see this. Right. So yeah, as we just heard, thank you for the introduction. So as you just heard, I run an online citizen science project that asks people like you to help us to find black holes. Black holes are some of the strangest and most extreme objects in the universe. They're objects that weigh at least as much as stars, but with all of their matter compressed into an unimaginably tiny space. And we don't actually understand what they really are. Our best theory that describes them is Einstein's general relativity, and it does a pretty good job of explaining how black holes look from the outside, but it's definitely wrong about what is inside them. And we know relativity is wrong, but we don't know what the right answer is yet, and that's why we need to find more black holes so that we can study them. Before we get on to finding black holes, though, let's talk about where black holes come from. Black holes are what is left when the largest stars reach the end of their lives and run out of fuel. But what does running out of fuel actually mean for a star? What is actually happening inside the star when that happens? Well, we'll start by recapping what stars actually are. Stars are basically big, hot balls of gas. They're mostly made of hydrogen, and they're held together by their own weight, by gravity. That's carefully balanced against the outward force from nuclear fusion reactions happening in their cores. The smallest stars weigh about as much as a big planet, and the biggest stars weigh 150 times what the Sun does. The Sun is our closest star, and it weighs as much as 300,000 Earths. Here's a video of what the Sun looks like. So while from here on Earth, the Sun looks like a smooth disk that doesn't really change, um, the reality is very different. The surface of the Sun is an incredibly turbulent place. It's covered in arcs called prominences, and there's hot gas welling up to the surface from deep inside. The Sun is a very active place. And what you see on the surface is only part of it. Inside of a star, there are different layers of material with gases moving around as the star's heat makes its way to the surface. And right in the middle is the core. That is where all the heat comes from, and it's where the very, very important nuclear fusion reactions happen. So in the core, the extreme pressure of all of the star's weight crushes the hydrogen and forces all its atoms together. Under all that pressure, the hydrogen atoms fuse together, so they join together to become helium in a process that looks roughly like what you see on this slide. Don't worry about the details that and the process isn't actually as simple as I've described. So it's a multi-step process where hydrogen atoms pair up with each other and protons convert into neutrons, and eventually a helium atom comes out of the other end. And I said that's very important, and that it really is, because it doesn't just stop at helium. If the star is big enough, it will go on to make every single other chemical element in the universe through a variety of different fusion chain reactions and one or two other processes that happen in supernovae. So you've probably seen the periodic table before. Here is one that's color-coded by where each element comes from, where each element is made, how each element is made. So the lightest two elements are hydrogen up here on the left and helium on the top right. They were created largely when the universe began in the Big Bang. Though, as I said, some helium has also been made in stars since then. And then most of the lighter elements in pink and yellow are made in the cores of stars during their lifetimes, and the red and blue ones are made in supernovae, which we'll come back to in a moment. Now that means everything around us was made, at least in part, in stars. The oxygen we're breathing, the carbon in the chairs you're sitting on, the calcium in your bones, they were all made in the cores of stars. The very atoms around us were once inside a star. And oops. Now, a moment ago, I said that the star's gravity is carefully balanced against the outward force of the nuclear fusion reactions. And the fusion reactions use hydrogen and other elements as fuel to make new elements. So what happens when those run out? Well, what exactly happens depends on how big the star is. But in every case, the first thing that happens is the core of the star starts to collapse, since the fusion that was holding it up, the outward force of the radiation and the energy released from the fusion that was holding up the core starts to slow down. So in turn, that then can allow new fusion reactions to happen involving heavier elements, because the pressure increases, so there's more energy available. So, for example, helium then makes lithium and so on up the periodic table. And for the first time, fusion can happen outside the core. So, if you remember the diagram I showed a moment ago with the layers of the star, um, just just outside the core are some additional layers where fusion reactions don't normally happen, but as soon as things start to collapse and the pressure increases throughout that region, suddenly fusion can happen in the outer layers, layers outside the core as well. Now, those two processes, the new fusion reactions and the new places where fusion is happening, can suddenly put a lot of extra energy into the star's outer layers. For smaller stars, those that are 8 times the mass of the sun or less, that causes the outer layers to expand and eventually dissipate as a planetary nebula, leaving behind what's called a white dwarf. A white dwarf is essentially the exposed, collapsed core of the star. Now, for heavier stars, the start of that process is the same. They start by expanding, but the process continues through the periodic table, creating larger bursts of fusion, which eventually lead to a supernova explosion. Now, that will result in either the formation of a neutron star, which are made of the densest form of matter. It's basically an entire star that's compressed down into one big atom made of neutrons, or a black hole in the case of the largest stars. So, supernovae are the absolutely huge explosions of those largest stars when they die. Um, they're far brighter than an entire galaxy. So the example shown here, you see the disk of a galaxy here. This bright dot here is a supernova explosion right on the edge of that galaxy. And you can tell just by looking at this that that explosion is brighter than everything else in that galaxy. So that's a lot of energy being released in a very short space of time. So in a way that makes sense that larger stars are capable of releasing more energy when they die, since they're bigger, right? There's more going on, there's more stuff available to release that energy. But what is actually happening inside those stars that's different to the smaller stars? What changes once you hit that 8 solar mass threshold? And the answer is exactly which elements are made at the end as the star's core is collapsing. So, as we've heard, all stars start out just using hydrogen to make helium. As they get older, they make heavier and heavier elements, working their way up through the periodic table. Now, at each stage, making each new element releases energy, and that's where the star's heat and light comes from, and that's what's holding the star up. But the energy you get out at each stage is less than at the stage before. So fusing two hydrogen atoms together to make helium releases less energy than you get by fusing helium atoms together to make lithium, and so on. And then that pattern continues all the way up to the elements around iron in the periodic table. Once you start making iron and the elements near it, you suddenly have a problem. At that point, the fusion reaction actually uses more energy than it releases, and you don't get any energy out anymore. The iron absorbs the energy that was creating the outward force from the fusion, and suddenly there's nothing left to support the star's weight. The core of the star collapses under all of that weight, with no fusion to slow it down, and as that happens, a lot more heat and energy is released in the areas around the core, and that causes the outer layers of the star to explode outwards. Now, if the core is heavy enough, it will collapse completely, unstoppably, to form a black hole, and otherwise it stops once it makes a neutron star. The outer layers are then thrown out into space by the explosion, and the resulting explosion is so bright that you can see it from clear across the universe. All of that energy allows the rest of the elements in the periodic table to be created. So everything heavier than iron, so for example the gold or platinum in a wedding ring, was created during a supernova in the final moments of a star at least 8 times the mass of the Sun. If that star happened to be over 20 solar masses, then the metal in your ring was created next to a new black hole as it was in the process of forming. And the black holes that supernovae make are usually themselves 8 or 9 times the mass of the Sun. So the star that makes them is 20 solar masses or more. 8 or 9 times that at least ends up inside the black hole. The rest is ejected in the explosion and sent out into space. The matter that goes into the black hole is compressed under its own weight, so much so that black holes are the densest objects in the universe, and we're not actually sure at what point that matter would stop collapsing. As far as we know, there's no force or mechanism that we can be sure about that would stop that collapse. According to Einstein, it never stops collapsing. Relativity predicts that it collapses all the way to a point of infinite density. Now, in reality, infinite density doesn't make a lot of sense. There aren't really any infinities in nature. A point of infinite density would have to have literally zero volume, and it would have to, so it would have to take up literally no space at all. And the maths of relativity doesn't really work once it reaches that point. So people call that point, that ultra dense point in the center of a black hole, a singularity. And originally, the word singularity was a mathematical term for what happens when your equations break and you get an infinity out as the answer. That's exactly what happens when you apply general relativity to black holes. The equations break. And often people assume that the infinities that you get out of that have some sort of physical significance. Really, that's unlikely, and that's why people are working on things like quantum gravity and string theory to try and solve that problem. So we know relativity can't quite be right. Excuse me. What we do know, though, is that whatever actually happens at the core of a black hole, all of that material, about 10 suns worth or more, is compressed so much that something very unusual happens. Black holes are so dense, as I'm sure you know, that anything that gets too close gets trapped, seemingly forever. Now, the reason that things get trapped has to do with escape velocity. That's basically how quickly you need to move upwards to get away from an object like the Earth, or a black hole, or a star, or whatever. And that has to do with the strength of gravity and how quickly it accelerates you downwards. At the surface of the Earth, the acceleration downwards due to gravity is about 9.8 meters per second squared. And that works out to a speed of about 25,000 miles per hour that you would need to reach from the surface to get into orbit. Now, the strength of gravity depends on how close you are to the center of the Earth or the sun or a black hole or whatever. If you were already halfway up into space, you wouldn't need to travel as fast to travel the rest of the way. But the thing is, with most normal objects like planets and stars, you can only get so close to the center until you reach the surface. You can't get any closer to the Earth's center than the ground without ending up inside the Earth. And as soon as you're inside the Earth, then some of the Earth is now above you, and so the planet's gravity can only get so strong before it stops getting any stronger. As soon as some of the Earth's mass is above you, it's no longer all pulling you down. Some of it's pulling you upwards, and it cancels out. So that's what's shown on the left in these two graphs. As you get closer to the center, the force increases until you reach the surface, and then the force of gravity starts to decrease again. But black holes are much, much smaller than normal objects. You can get much, much closer to the center of a black hole without ever reaching a surface, because there is no surface. That means the gravity can get much, much stronger, and the escape velocity can get that much higher. So as shown on the right, the force of the gravity, and so the escape velocity, just keeps increasing all the way down. And that means black holes look something like this. As you get closer to the black hole, you reach a point. So the black hole is here in the center. And then as you get closer to the black hole, the escape velocity goes up, and then you reach a point where the escape velocity suddenly equals the speed of light. And that's the point of no return. If you cross that point, there's no turning back because nothing can travel faster than the speed of light, so you can't reach the appropriate escape velocity to get away. That point's often called the event horizon because we can't see anything, events that happen inside of it because the light from inside can't get out. And then all sorts of weird things happen in the equations of gravity once you get inside there. Time and space swap places and all sorts of funny things. But that's the key point is that because there's no surface, you can get so much closer to the center of gravity that the escape velocity can reach these sorts of extremes they couldn't do with a normal object. Now, the three kinds of objects I mentioned a moment ago, the white dwarfs, the neutron stars, and the black holes, are collectively called compact objects because they're all formed from normal matter that has been compacted by the force of gravity beyond the point that matter normally would be. And of course, we're interested in finding all of these things because they're all interesting. In particular, black holes in my case, but white dwarfs and neutron stars are interesting too. And if you're interested in finding these things, you might naturally ask how many of them exist today in the Milky Way, waiting for us to find them. And we can roughly estimate that. So we understand roughly how stars form, we understand how they evolve during their lives, how they end their lives, and what they create once they end their lives. And we understand what the star formation rate of the Milky Way has been throughout its history. So if you put all that together, you can work out how many stars formed over time, how long each of those stars would have lived, and what those stars would have created once they died. And if you do that, you work out that there should be billions to tens of billions of white dwarfs, hundreds of millions or billions of neutron stars, and millions, tens of millions of black holes, with some number of those existing in binary systems in orbit around either another black hole or a neutron star or a white dwarf or a normal star. So you might think that in a binary system, when the supernova explosion happens, that the companion star would be destroyed or that the binary would be disrupted and they would go their separate ways. And in some cases that does happen. But in a surprising number of cases, the binary can survive, the companion star can survive. Their orbits may change, things may get reconfigured, but you can still end up with a post-supernova object like a neutron star or a black hole in orbit around a normal star. And that's important for what we're going to be talking about in a moment. The exact numbers are open to debate, but it definitely happens in a large percentage of cases. So just talking about the black holes in the Milky Way, we know about, we know for sure about 20 or so of them, and there's about another 50 candidates. So that leaves a lot of undiscovered black holes out there in the Milky Way. If there's 10 million of them in total, we know about less than 100. There are loads waiting to be found. Almost all of the ones we know about were discovered through X-ray observation, but because they happen to be very bright in X-rays because they're accreting matter, meaning they're pulling matter in from nearby stars. Only about a handful of what are called quiescent black holes are known. That's black holes that are not accreting matter, black holes that are just quietly sitting there, not pulling in matter and therefore not emitting large amounts of radiation. And those were all discovered recently. That includes both one black hole, which is completely isolated on its own, and a couple of candidates that exist in binaries. Um, so this is a huge gap in our knowledge of stellar evolution. This graph, by the way, actually explain. So this shows in blue the expected population, how many we expect to exist. The X-ray binaries are most of the ones we know about. There should be about 1,000 of those in the Milky Way. We know about 70 of them. We're actually not doing too badly there because there should be 1,000 in total in the galaxy. Some of those will be on the other side of the galaxy where we're not going to be able to see them. So finding almost 10% of those isn't too bad, and they're quite easy to see because they're very bright in X-rays. And then obviously the rest of the population we found almost none of. This graph is on what's called a logarithmic scale. So each line on the graph is 10 times the value of the line below it. So step up from one line to the next. That's 100, that's 1,000, and then 10 million up here at the top. So it might not look like a big difference on this graph, but you have to plot it this way to have this huge difference shown next to the next to the X-ray binary population. So that's what I work on. Is we are the team I work in are looking for quiescent black holes which are in binary systems through something called self-lensing, which we'll get back to in just a moment. So just a little bit more explanation on black holes and how we detect them. You might think that since black holes trap light, there would be no way you could see them. But there are a number of ways that black holes can affect their surroundings, and those are often quite easy to see. So we've already mentioned the X-ray binaries. As I said, there are about 70 of those that we know about in the Milky Way. They were all detected because the black hole is pulling in material from a nearby star, as shown in this artist's impression. Now, the reason that makes them very bright in X-rays is that the material that's being pulled off of the star is flattened down into a thin disk called an accretion disk that's rotating very, very quickly around the black hole near the speed of light. So there's a lot of friction, a lot of tidal forces. That makes it very, very hot. And that means that the material is emitting X-rays as it falls in. So it's kind of like how a piece of hot metal glows red. If you get it even hotter, it'll glow blue. If you were to get it hotter still, it would glow in ultraviolet light. And if you heated it to millions of degrees, it would glow in X-rays. I don't recommend trying that in your kitchen, but that is what happens around a black hole. And that disk of material it is emitting the X-rays that we're able to detect from here. Now, a lot of things in space emit a small amount of X-rays, including stars like the sun, but the accretion disk is so hot and so bright that it completely outshines all of the other X-ray sources in the sky. So when you do an X-ray survey of the sky, which you have to do from a space telescope because X-rays can't get through the atmosphere, luckily for us, if you do an all sky X-ray survey, the X-ray binaries just stand out because they're very bright against the background. So that's how we know about most of the black holes that we can detect. Now, we can also, if we can't see the black hole itself directly, we can also see how it's affecting the orbits of the things near it. This is actually a time-lapse video of the center of our galaxy, and you can see the stars moving around the seemingly empty space where the central supermassive black hole is. So this isn't quite the same kind of black hole that I'm looking for. I'm looking for the smaller stellar mass ones. The black hole at the center of our galaxy is a supermassive black hole, but the gravitational effects are the same. You can see the stars orbiting around the black hole. And we can see the same kinds of effect with smaller black holes. We probably won't be able to resolve the individual stars in images because everything's much closer together. But we have ways of measuring the speed of stars, and we can see the orbital motion of the star, even if we can't see the thing that's orbiting. And luckily for us, the way that gravity works out, you can work out the mass of the unknown object that the star is orbiting just by measuring the speed of the star's orbit. You don't need to know how massive the star is, even. You can just measure how quickly the star is orbiting this seemingly empty point, and you can work out how much mass has to be in that point. So you can work out how massive the black hole is. And in the case of the black hole at the center of our galaxy, Sagittarius A star is over 4 million times more massive than the Sun. Very, very different scale to the black holes that I'm looking for, but the effects all just scale up. It's the same effects. And then finally, we can detect black holes through something called gravitational lensing. Gravity doesn't just pull objects towards each other. According to relativity, massive objects bend the space around them, and then light follows that curved space. That means massive objects can deflect light. Now, in principle, all objects do that a little bit, even things like a person or a car or whatever, but it takes a big object for that to be measurable. So this image is an example of a galaxy, and it's this reddish blob in the middle is the galaxy. It's what's called an elliptical galaxy, because of its shape. And that's bending the light of a much more distant galaxy. This arc you see around here is the focused light from a more distant galaxy. It's somewhat distorted into a horseshoe shape, but it's it's still, we can still study that, and that is light from a galaxy that we would not otherwise be able to see. It's too far away for us to see, but its light has been focused like a lens by this foreground galaxy, allowing us to study it. Now, again, this is a galaxy producing lensing. What I study is the same thing, but on a smaller scale. So it's not just galaxies that can do gravitational lensing. Individual objects like stars and black holes can produce gravitational lensing too. It's physically the same process, but on a smaller scale, and we call that microlensing. Now, in the case of microlensing, we can't see the focused images. So we don't see a nice focused ring around the lens like we do there. What we see is just a magnification of the background star. So if you have something in this animation, it's actually a planet. Microlensing is often used to find exoplanets, but you can imagine that's a black hole as well. As that passes along a line of sight between us and a star, it bends and focuses the star's light into an image around the black hole. That image is too small for us to see, but because extra light is now coming towards us, it produces a magnification of the star that we can measure. And that gives away the presence of the lens object, even if it's something that we can't see directly. Now, I look for a special case of gravitational microlensing called self-lensing. That is when the lens and the lensed object, so the star and the black hole, are actually in a binary orbit with each other. So normally in microlensing, the foreground lens and the background star have nothing to do with each other. They could be tens of thousands of light years apart. One just happens to be moving across the line of sight of the other one. It's complete chance alignment, a one-off. But sometimes, if you observe enough stars, you get lucky and you see these kinds of events, and you can study the lenses. What I'm looking for are lenses that are in a binary orbit with a star. Again, physically the same thing. All it means is that the lens and the source are much closer together, and they have to be lined up edge on so that they transit in front of each other from our point of view. Now that means a couple of important things when we're looking for these events. The amount of magnification that you see depends on how big those lensed images are. So if you imagine this black hole here, that this image here around the arc around the central galaxy, the surface area of that image, so how big that image is, determines how much extra light is coming our way, how much extra light is arriving at our telescopes. So in the case of self-lensing, where the source and the lens are much closer together, that makes it a little bit trickier to spot these because the size of that image depends on the distance between the source and the lens. So the further apart the source and the lens are, the wider that arc is, and therefore the surface area is larger, meaning there's more magnification of the source's light. So in our case, where the source and lens are very close together, those images, even though we can't see them, those images are very small and we get less magnification. So with a normal microlensing event, you might see the background star changing in brightness by several magnitudes. You know, it might go from magnitude I don't know, 14 to 12 or something, and suddenly you see a very noticeable increase. In our case, we're looking for self-lensing systems where they're close together, and we see a much smaller increase in brightness. So that makes it more difficult, but we're lucky because the source and the lens are in orbit with each other, suddenly we're looking at periodic events rather than one-off chance alignments. So once per orbit, we can see the lens, we can see the magnification from the lensing event. Now, the orbital period can be anything from a few days to thousands of years. So it's only in the closest orbits that we can see the repeating events. But that is something that is very useful. As you can see, if you see a periodic lensing event, you know it has to be self-lensing. And also because the distance where the lensed images, it's called the Einstein radius, because that is so much smaller for these systems, it's actually only possible to have self-lensing if the lens is a compact object. So it has to be a white dwarf, a neutron star, or a black hole, because all other objects are too big and they would block the lensed images. The surface of the object would block the lensed images. So the bottom line is, if you see a repeating microlensing event in the brightness measurements of a star, you know that has to be self-lensing, and you know therefore that the lens has to be a white dwarf, a neutron star, or a black hole. So this is potentially a very useful way of finding compact objects that we wouldn't otherwise be able to detect. And that's what I work on. So this is the Black Hole Hunters project that I run on the Zooniverse platform on zooniverse.org. This lets anyone with a phone, a tablet, or a computer join in the search for black holes by looking for these gravitational lensing events in measurements from the TESS satellite. So TESS, pictured here before it launched, is a space telescope which is designed to find planets around distant stars using something called the transit method. It does that by measuring how bright stars are repeatedly over and over again, and then looking for times when a planet passes in front of that star and blocks some of the star's light, so the star gets dimmer, and then from that you can work out where there's a planet there and how big the planet is, and all sorts of useful data if you're interested in studying planets. Now, the data that that telescopes like TESS produce is fantastically useful for a whole range of other things. By taking repeated measurements of the brightness of stars, they give us a wealth of information about the stars themselves and about other things that are happening nearby to those stars. In our case, that means we can use that data to look for the microlensing events that we are interested in. Those events look a little bit like this. So imagine this is a graph showing how bright a star is over time. So along the horizontal, you're dealing with time. So as you move from left to right, time gets later. And on the vertical is a measure of how bright the star is. These are called light curves. These ones are actually simulated, but these show what self-lensing events in the test data will look like. So these are simulated such that they're very realistic in terms of looking like the real data that comes out of tests. And you can see there's a range of different shapes that we're looking for. So we get very, very big big curves, big peaks like the one on the top left, and then also runs the whole range down to very tiny little short little spikes like the ones we see on the bottom there. Um, so these are the kinds of things that we're looking for. Self-lensing events can look at anything like any of these or anything in between. So there's a range of things that we're asking our volunteers to look for. And we show our volunteers examples like this, and then just ask them to label anything that looks like these. And the other key thing is that these are all symmetrical. So we ask them to look for symmetrical peaks in the graph that look like the examples that they've seen. And this is what it looks like on the Zooniverse website. So we show people a snippet of a light curve, and then they highlight on the graph anything that they think looks like the examples that we've shown them. And then every graph gets shown to more than one person, so it doesn't matter if someone makes a mistake or if they're not sure, or if someone just submits nonsense just to be disruptive. That does happen, unfortunately. We can catch those mistakes when we put everyone's answers together at the end. So you don't have to be an expert. You don't have to worry about making mistakes. You can just turn up and do your best. Every contribution is useful. So this project's been running for a few years. In that time, we've had these numbers are about a month old actually, so the current numbers are probably a little bit higher, but we've had almost 18,500 registered volunteers take part in the project, and as well as some unknown number of anonymous volunteers. You don't have to be logged in to use the Zooniverse, so we don't know how many people have used it without logging in, but there are definitely a lot of those as well. And between them, they've submitted well over 7 million classifications, where a classification is one single answer about one portion of the light curve. And they've completed well over 400,000 subjects. So a subject is one graph that we show to people. So you can see from these numbers, we show each one to lots of people. We get many classifications for each one and put them all together. And here are some examples of the kinds of things that our volunteers have found so far. These are some of the candidates that we're currently investigating. We haven't vetted these, and I can't claim that any of these are microlensing events now. We're still investigating these, but these are promising looking. These are the kinds of things that we're hoping to find. So we start with this one on the right-hand side. You can see highlighted in green is an event that the volunteers have labeled where there's one single spike in the graph. And then these other two are very interesting because they seem to be periodic, which is what we're looking for. The tests, light curves, are all 27 days long. So this one that's just a single peak could still be a periodic signature that just, the period is just longer than 27 days. But these two on the left are interesting too because they seem to be periodic, and it's not obvious from these what's causing that. There could be lots of other things that could cause this sort of light curve, but self-lensing is certainly on that list. So we're investigating these at the moment to see if they might be the events that we're interested in finding. We're also, now that we have millions of these kinds of classifications, we're now looking into how we can train machine learning algorithms, aka AI, as it's called these days, to look for these things for us. So a key philosophy of Zooniverse projects is that you don't want to waste people's time. So it's not probably the best use of people's time to ask them to keep doing something that they've already given us millions of examples of. We're at the point now where we have so many examples of labeled light curves that we should be able to train machine learning algorithms to look for those automatically, and then we can free up our volunteers' time to do the later parts of the process, the vetting of candidates that we currently can't automate. So we're currently using something called deep learning. This uses something called convolutional neural networks. This is something that I'm working on as we speak. We're still in the process of getting this all working. So the phrase convolutional neural networks is a bit of a mouthful. I wouldn't expect anyone to know what that means. A neural network is just a type of learning algorithm that's roughly designed on how a brain works. We have different different little modules called neurons that talk to each other, and there are weights, and you train it by example. So you show lots of examples of things you're looking for, as well as lots of examples of things you're not looking for, and then it learns automatically how to distinguish between the two. And convolutional just means that it takes sort of a weighted sum of outputs from different things. Um, so basically, it's trained to look for lots of different patterns, and then so it has lots of different parts of the network that look for different patterns, and then it puts the outputs of those together into a weighted sum to come up with a final classification. So, for example, in the example shown in this diagram, it's looking for robots. So there'll be a bit of the network that's trained to look for the hand. There might be another bit that's trained to look for the eyes or the ears or whatever. So each little part of the network learns to look for a specific shape in an image or a pattern, and then it puts all those together. So we're training these now on two things, on the simulations. So these simulations I showed you are the exact ones that we're using to train a neural network, and it will learn to recognize these kinds of shapes in the graph. And it seems to do pretty well at that. We're also training or about to start training another neural network on the volunteer classifications directly. So we'll have one that's trained on simulations and one that's trained to think like a human based on the volunteer classifications, and then we can put the answers from those together to come up with a final classification. And the idea is that the overall process will look something like this. This is a process, an idea called active learning, where you take your machine learning, you show it to people to get feedback, and then you put that feedback back into the algorithms in a loop to train it all to get better over time. So the idea is that we start by training machines on the simulations and on the data that we already have. We filter a whole bunch of data with those algorithms. That's what we're doing at the moment. As we speak, I have a server in Southampton that is crunching through all of the data from tests and to apply our initial machine learning models to it to see what we can find. Once that finishes, I'll get all of that data up on the Zooniverse. The most promising candidates can go to the Zooniverse, and then we'll ask the volunteers to help us filter those to remove things that are false positives, things that are not the events that we're looking for. And then we'll take some follow-up observations and make some tweaks to the data, and then feed all that back into the machines at the end. And then hopefully, over time, the machines get better and better at finding the things that we're interested in and ignoring the things we're not interested in. And also, they'll get better at ruling out new types of false positives. So every time we go through this loop, we can ask the volunteers to help us filter out new things that the machines are getting confused on. So each loop, the machine won't get confused on the things it was confused on the previous time. It will learn from the previous time and do better. But there will always be new things that we need to tweak and that we'll need the help of humans to filter out. So that's what I'm working on at the moment. Hopefully, in a year or two, I'm hoping to have some results to show from this. I didn't mention before, but actually the self-lensing systems that we're looking for are there's only 5 of them that are known in total, and those are all white dwarfs. So we are hoping to be the first people to find self-lensing black holes, and potentially that could be an exciting new way to find new black holes that we haven't found before. Might be it might turn out to be nothing, but it might also be a really useful tool in the search for black holes. And hopefully you'll agree that that would be pretty exciting. So that's what I'm working on. I'm happy to take any questions if anyone would like me to answer any. Thank you.
Thank you very much, Adam. I'm sure everyone will agree that very interested in what you're doing there, especially because it's citizen science. You know, it's something that everyone can get involved in. Could I just ask you to stop sharing your screen for a moment, and that way you can see the lovely faces of the audience as we light up the room again and double check that no one nodded off? No, no one's nodded off. Excellent. That's a good start for questions and answers. So What we have is we have a Roy Gunson with a pokey stick and a microphone on. We will accept questions from online. Put a digital hand up, please. And from the room, put a non-digital, more analog hand up, please. We have Mike online. So if you'd like to unmute, show us your pretty face and ask your question, please.
Hi, Adam. Fascinating. Couple of questions, if you wouldn't mind. How would you differentiate between a solar event, like a flare causing a brightening, and a microlensing event where the period of that microlensing event is so long as not to be repeated in a sensible time frame?
That is an excellent question because flares, so stellar flares are actually one of the biggest false positives that we have because they do look almost exactly the same as the events that we're interested in finding. Most stellar flares are asymmetrical, which is useful. So they suddenly increase in brightness and then they gradually get less bright. Whereas the events that we're interested in are completely symmetrical, more or less. But you do get atypical flares which look symmetrical, or nearly so. So that is an ongoing problem. We're still working on that.
So not easily then.
Not easily. But I mean, so confirming self-lensing systems, ultimately what we need to do is take spectroscopic observations and then we can measure things like the velocity of the star and confirm that it's in orbit around an unseen companion. So at the end of the day, the follow-up observations would always differentiate between the two, but ideally we don't want to waste our time taking follow-up observations of something that's just a flaring star.
Yeah, that's great. Quite a quick follow-up. What's the lower limit of black holes that you can detect with this microlensing, and how does that affect the limit of the inclination relative to us where microlensing can be affected?
That's a good question too. So in principle, any size black hole could produce a microlensing effect. The brightness of it would depend on the mass of the black hole, but it is more dependent on the distance between the source and the lens. So probably, don't know any numbers off the top of my head, but probably even a primordial black hole could in principle, the very tiny black holes could in principle create a microlensing effect if there was enough distance. Probably not in a self-lensing system. They wouldn't be far apart enough. But there isn't really a hard lower limit. I think it would depend more on the limits of the telescope we were using and what it's able to detect.
Okay, thank you very much. Thank you.
Thanks, Mike. So again, digital hands or physical hands. There's one at the back. Anthony.
Hello, thank you. Are black holes partially made from dark matter, or totally in some cases, or not at all?
I suppose I mean, there must be dark matter. So, I mean, the key property of dark matter is that the one force from nature it obeys is gravity. So, yeah, dark matter should end up inside black holes in some amount. And actually, that does it's not really part of my work, but it's an ongoing question in cosmology is how is it that supermassive black holes got as large as they are in the time available? There isn't really enough time for them to have grown through the normal processes. So there are people looking into whether or not dark matter could play a role in that, whether or not they could accrete dark matter at a faster rate, and so on. So yeah, I think the short answer is yes, probably there should be dark matter inside black holes because dark matter should be everywhere and should be captured by their gravity.
No.
Can I ask another question?
Of course, yeah.
Could the chirality of galaxies nearby indicate the location of dark matter?
I think the short answer there is that that is well outside my area of expertise. I'm not an expert on dark matter at all, to be honest. So I'm not sure I can really answer that.
Good, safe answer.
Safest not to guess, I think.
So, any
I've
other?
got
Go on then, Roy.
just one that's popped into my head. You were talking about the signal being symmetrical from these. Somewhere at the back of my head, somebody was talking about rotating black holes, which twist the space-time in the locality. Would that twist the light signal going around the black hole and make it skewed in some way?
You guys are asking some really good questions like that. That is actually, yeah. So that's I think that's something that my boss Matt Middleton was interested in looking into, is the effects that the spin of the black hole could have on the shape of the light curve. So that, yeah, that is plausible. That is it would be a very small effect, but in principle, if we were to find some of these systems, then that is one of the things that we could look into.
As I say, it just popped into my head while you were talking. And
Any other questions online? I've got one. So, given how many non-accreting black holes should exist in the Milky Way, how confident are we that the microlensing and self-lensing are actually going to realistically close that detection gap?
I would say we're fairly confident. I mean, some of my colleagues have done estimates of how many of these systems should be detectable in various surveys. TESS actually is probably going to detect the fewest, but we're starting with it because it's just because of the way it observes. It is the one that's likely to detect the most interesting ones. But surveys like the Vera Rubin Observatory, for instance, that's going to run for so long that it should find loads of these events. It's a 10-year survey. So I mean, we know for sure that these systems should exist, and we know we've done estimates of the numbers. So all we've really got to do is actually crunch the data and look for them, and we should find them. If we're not finding them, then something is seriously wrong in our understanding.
Back to the blackboard.
Yeah.
Back to the drawing board, I suppose. Like
Yeah.
all science. I mean, the other sort of question I have is obviously, so iron's normally the chemical that becomes the tipping point. Why isn't it a different element? Why is it iron?
I guess that's really a quantum physics question. It's just the amount of energy that is sort of. So when you form an atom from a bunch of protons, the combined mass is not exactly the sum of the mass of the protons. So if you put two protons together to make helium, you get some energy out because the helium atom weighs slightly less than all the protons that went into it, and that energy comes out as radiation. Just because of the way that the physics of that works out, that mass difference is smaller as you go up the periodic table until you get to iron, then it flips. That's why you can get energy out from fusion, but you can also get energy out from fission if you take uranium or plutonium, for instance. So it comes out of the way that the protons bind together in the end.
So Mike did just jump in just before you, Tony. So Mike, your next question.
Yeah, a couple of points. First thing, Loz, if you look up binding energy of atoms, that will give you the answer to your question. It's all to do with, binding energy. Just Google it, mate. Question. Oh God, I forgot my bloody question now. I was thinking about yours.
Yay!
Oh God, I'll come back to you.
Fair enough. We'll have a Tony in between then.
Hi. You spoke about using the test satellite. Is there any chance to using data from Gaia?
Yes, that's interesting. So the Gaia, even though the survey's ended, they haven't released their final data yet. They're still working on it. And they are going to be releasing a set of light curves covering the entire duration of the survey, which is potentially interesting, except it's not. We'll look at it, but it's probably not the ideal data set because Gaia wasn't really primarily designed to produce that sort of data. So something like TESS is specifically measuring the brightness of stars, and it's the way it observes is set up so that it does that. Um, it's measuring every star every few minutes, and then it moves on to a new field of view. Whereas Gaia was observing the entire sky continuously, so that the data points are much more spread out, and it's not really optimized for doing that sort of thing. But yes, they will be releasing some light curves and photometric measurements that might be useful as well. With that, it's really going to be a case of if we got very lucky and Gaia happened to point in the right place at the right time, then maybe if it saw something. But yeah, our strategy is basically we're starting with tests, but we're planning to just get data from every single survey we can get our hands on, and cast as wide a net as possible, basically.
Okay, so from the test data, what's the cadence of revisiting a section of the sky?
Well, there's two cadences to think of. So what the way TESS works is they've divided the sky up into sectors. They observe each sector more or less continuously for about a month. So they take measurements every couple of minutes or every 5 minutes of every star in the field of view for a month. But then move on to the next sector for a month, and then the next sector. So every few years they come back to sectors that they've already observed. But while they're observing a sector, the cadence is fantastic because it's every few minutes.
So does that cadence fit in with what you need, or are you using that cadence because that's what you've got?
Um, that cadence is really good if we're interested in finding the shortest period events. And also because TESS is so sensitive. So I didn't point it out during the talk, but the shorter the orbital period, because the distance between the source and the lens is smaller, that means the shorter orbital periods have the smallest magnifications. So the things that are the hardest to see in terms of how bright they are the easiest to confirm by looking for the repeats. So what we want is something that's very high cadence, but also very sensitive to try and find those systems, and that's really where TESS is ideal for us. With other surveys, we're more likely to find other orbital configurations. So it's really a case of like each survey is good for looking for a different part of the population.
For the very small magnitude changes, are they milli magnitudes, or are they bigger?
I think yeah, we're talking a few percent sort of change in brightness. So yeah, tiny amounts really.
Okay.
Okay, Mike, you can come back in if you've
Yeah, I've remembered.
remembered.
I remembered and I wrote it down so I don't forget.
That's what I'm happy to do.
Does the microlensing affect red or blue shift? And if it does, could this be a way to narrow down your search and remove false positives?
What's interesting about microlensing is that it's completely unaffected by color. So you might see some red or blue shift effects. Actually, would you? That's interesting. I don't know actually. You don't see effects. So like with something like a flare or a stellar pulsation, you see different changes in brightness at different parts of the spectrum. That you wouldn't see with microlensing. I wonder if I don't know offhand how big of an effect the gravitational redshift of the black hole would be. I suspect it would be very small. I can't give a definite answer off the top of my head.
Something to think about, maybe.
Yeah.
Okay, thank you.
So I don't know whether I'm going to ask the second one, but certainly the first one, I I will. So I think it's more of an opinion piece than anything. So are we actually more limited in our detection methods or our theoretical understanding when it comes to detecting black hole populace?
I think our theoretical understanding is actually really good. So I think it's definitely a case of being limited by how hard it is to actually look for these things. So like you see lots of papers where people have estimated, such and such a type of black hole would produce some very small signal in a particular kind of data, and then it's very hard to actually detect that to confirm it. But we can predict that those things should happen. So yeah, I would say definitely it's not the theory that's holding us back, it's the practical side of actually detecting them.
Okay. My second question is a little bit, I don't know, just rattling around a little bit, and I might have got the wrong end of the stick. So if singularities are where our understanding breaks down a little bit, what observations would help on quantum gravity and general relativity?
That's a very good question that I don't think I'm qualified to answer. Yeah, I'm not really sure, to be honest. Yeah, I'm not really up to speed on what the predictions from those would be. I think that sorry, have you frozen? I think you might have frozen. Is it me or is it you? Oh no. Yeah.
I'm just really good at sitting still. Sure.
Yeah, I think I think once you get very close to the black hole, there might be some differences that might be detectable in effects from things like the spin, but I'm not completely sure. I wouldn't want to guess.
Okay. I've done my brain rattle. If you leave me any longer, I'm going to start thinking.
Nobody else got any questions? So at that point, I would like to thank Adam for quite an interesting talk. I think we've bamboozled in a few questions in the end, but I think we've enjoyed the talk on black hole hunters. I understand there's a website you might have to encourage people to join your online hunters. So if you want to send me some details, you've got my email address. Just send it along, and I will pass it along to our members, and some may be interested in joining you in finding these little transient blips in star signatures.
Great, yeah, I'll send that over right after this.
So it just leaves me to say, can we thank, in our usual way, Adam for such an interesting talk?
Thank you.